Okay, so the last speaker of the cryptanalysis session is Mark Wostermans, who will be speaking about analysis of REDOG, the Pad Thai attack.
Thank you very much for the nice introduction. So my name is Mark, and in this talk I will tell you something about our work, the analysis of REDOG, the Pad Thai attack, which is a joint work with Alex Pellegrini. So REDOG, standing for Reinforced Modified Dual Ouroboros based on gabardine codes, long name, is a rank metric public key encryption scheme that was introduced by Kim Hong Lau and others in 2022. And the motivation for us to look at this scheme was that it was a candidate in the KPQC, the Korean Post-Quantum Cryptography competition, that Monica also mentioned in her talk yesterday. So when we were working on this attack, it was actually Alex that was responsible for the cryptanalysis part, and I was mainly looking into the security proof of REDOG. But at some point, Alex came up to me and he was like, I'm pretty confident that I have an idea to not break the scheme, but to attack it. And I joined his side, and eventually we came up with the Pad Thai attack. So let's start off with a little bit of background information that we need on the rank metric. So we start off with a basis, alpha 1 up to alpha m, and let that be a basis of f2 to the m over f2. And what we can then do is we can represent, or we can express each element in f2 to the m as a linear combination of these basis elements. And then we use these coefficients as a representation for the element x in f2 to the m. And now we define this map called mat, which constructs a matrix where we input a vector of elements in f2 to the m, and then the matrix is constructed by determining the representation and putting those in as columns into that matrix. And now we have enough information to define the rank weight. So the rank weight of a vector v is given by the rank of that matrix induced by v. And additionally, we define the rank distance between two vectors v and w to be the rank weight of the difference between these two vectors. Now a very little bit of information on rank metric codes. So a rank metric code C with parameters n, k, and d is a k-dimensional f2 to the m linear subspace of f2 to the m to the n with minimum distance d, where we compute the minimum distance by taking the minimum over all rank distances between any two distinct code words in our code C. And the correction capability is equal to r, which is the floor function of d minus 1 over 2. And I will not mention a lot of information about the rank metric codes in general or about gabardine codes, which will be used for REDOG, because we will use them as black boxes anyway. So I don't want to bother you too much with this background knowledge. So let's have a look at REDOG. So REDOG consists of 3 algorithms. We first have the keygen algorithm that outputs a public key and a secret key. So let's go over what they look like. So the public key is the public key consists of 2 matrices, being M and F. Matrix M is a matrix generated uniformly at random. And matrix F is a product of some matrices. So we have the matrix M again. We have the inverse of P, where P is an isometry. We have H1 and H2. And if we concatenate them into a matrix H, then H is the parity check matrix of a gabardine code. So that's where the gabardine codes come into. And then we still have this matrix S, which is generated in sort of a special way. I do not want to dive into too much of the details there because we will not exploit its structure, but it's generated using a technique introduced by Ledrow at PQCrypto in 2017. For now, I only want to mention that it is an invertible matrix because we will need that later in the decryption algorithm. And then the secret key, it consists of these matrices P, H, and S, together with a synonym decoder that can correct up to R errors. And now the idea is that if you're given F, then it's hard to recompute these P, H, and S. So it really is that P, H, and S are matrices that are secret. So now let's look at the encryption algorithm. We input a message together with a public key. And in the first step, we generate an error vector. And this error vector consists of 2 components, E1 and E2, where it's given that the rank weight of E1 is equal to some publicly known value T1, and the rank weight of E2 is given by T2, which is also publicly known. We hash the error vector and add it to our message to sort of blind it, and then we compute the ciphertext components by multiplying M with big matrix M and add E1 to get a component C1, and we get a component C2 by multiplying M with F and adding E2 to that. And that gives us a ciphertext. then to decrypt such a ciphertext, we first make some small computations to obtain the C prime, which is equal to E prime times H transposed. And because H is the parity check matrix of a capital link code, and by construction, E prime has rank weight at most R, we can apply the syndrome decoder to recover this E prime. And then we see that, well, E prime is equal to E1 times the inverse of P, and the second part is minus E2 times the inverse of S, so we can use P and S to recover E1 and E2. And as soon as we've recovered E1 and E2, we can recover our message. So now that we know how the REDOG system sort of works, let's have a look at the attack. And the main idea is as follows. So we are given, so it's a message recovery attack. So we are given the ciphertext, public keys, and we aim to recover the message. And we can see that the ciphertext, it's constructed by, so we have a little system where some error is being added. And now what we are aiming to do is we are aiming to convert that system into a new system that uniquely solves for the same message, but that does not have any errors. And what allows us to do this is that the rank weight of E1 and E2, so to already spoil that, it's relatively low. To give you the actual number, so the authors of REDOG, they gave parameter sets for 3 security levels, being 128 bits, 192 bits, and 256 bits. And T1 is equal to 6, 12, and 15, respectively, for the security levels, and E2 was 2, 2, and 3, for the respectively for the security level. So it's really E2 being very low here that makes this attack successful. And it sort of consists of 3 steps, the attack. So what we do is we first utilize the lowest rank weight of E2 to construct many equations for a system. Then we will observe that we don't have enough equations yet, so we will still have to add some others, and we use E1 for that. And in the end, we construct a system and we recover M. So how do we construct these error-free equations? So now, instead of looking at the full system, let's look at a single equation. So we know that a ciphertext component is computed by taking a message M, we multiply it with a corresponding column of, in this case, the matrix F, so this is for C2, and then we add some error term. And now let's assume that we will be able to find another equation which has the same error term. Well, we work over F2, so what we can do is we add those 2 equations, and then we see that the error term vanishes. And now the idea is that we have the publicly known ciphertext components, we know the columns of F, that's a publicly known matrix, so we can construct an equation that is error-free and that solves for M. And this is what we are going to do in the attack. So let's give a little example for the first step. So, as I said, for the lowest security level, which is 128 bits, we have that the rank weight of E2 is equal to 2. And that means that each value in the error vector can attain at most 4 values. We don't know these values, but we can in this case represent them by using 0, alpha, beta, and alpha plus beta. And now let's say, for now, that we know what the error vector looks like. So first, we will cover how can we construct equations if we would know the error vector. Well, in this case, we have a look. So we see that the first entry of the error vector and the second one, well, the error is already 0. So there's not much work to do here. We can simply add the corresponding equations to our system. Then we have 2 error entries in the error vector being alpha. So what we could do is we could add those so that the alpha would vanish and we have an error-free equation. So that's the third equation on the slides. Then we have this beta, and yeah, unfortunately there's no other entry which has an error value equal to beta, so there's no equation we can add for that one. But for the last one, the alpha plus beta, we can take 1 entry corresponding to alpha, 1 entry corresponding to beta, and add the corresponding equations. And now we see that for this error vector, it has size 6. We can construct 4 equations in total, and generally for an error vector, so the error vector size n minus k, and we will observe that we can construct n minus k minus t2 equations because, well, we can construct 1 equation per entry being 0 and per entry being alpha plus beta. But for the alphas and the betas, every time there's 1 entry with this technique where we can't construct an extra equation for, so we will lose 2t equations here. But yeah, this is all nice, but of course we don't know what E2 looks like in the attack. So how will we do this for the attack? And first I have to introduce the concept of an arrangement here. So an arrangement is sort of an order representation for our error vector. So in this case, the arrangement of E2 with respect to a certain basis is given as follows. So we have this first set containing 1 and 2, and these correspond to the indices that have the error value being 0, so the first and second index of E2. We have 3, 4, which corresponds to the indices of where the error vector, the entry in the error vector is equal to alpha, our first basis element in that small basis. 5 corresponds to the entries that have as error value beta, and then 6 corresponds to the linear combination. And now for our attack, we are going to iterate over all possible arrangements, construct the corresponding equations using this technique, and then in the end we can check if we have a full system whether the system is error-free. So we'll already say that we are not able to check per individual equation whether it's error-free, so that's why we iterate over all possible arrangements. But yeah, as I already said, so we do not have enough equations yet to solve uniquely for M. And what we're going to do is we are now going to use M, C1 and E1 to construct the remaining equations. And you might be wondering, well, can't we just apply the same technique as we did before, where we just sort of iterate over arrangements to guess what E1 looks like? But T1 is a bit higher than T2, it will become too costly. And also, we don't need that much equations anymore. So we will use another idea. We know that the rank weight of E1 is equal to T1. And that means that if we would take T1 plus 1 elements from the error vector, then that set must be linearly dependent. So there must exist some linear combination of these elements so that the error term will vanish. So if we add equations according to that non-trivial combination of zi's, then we obtain some equation that is error-free again. And now we are going to repeat this process for each equation that we still have to pass to our system. So we would need T2 plus 1 extra equations. So we are going to take T1 plus 1 linearly dependent sets of, we're going to take T1 plus 1 columns of M and corresponding ciphertext components. We're going to iterate over all these linear combinations and repeat this process T2 plus 1 times. So to sort of wrap these steps up, so in steps 1 and 2, we're iterating over an entire, we're iterating over all these arrangements, we're iterating over all these linear combinations, and we obtain some system. And this is the moment in time where we're going to check, is this system solving for our message M? So what we will be doing is, we will solve this system, and for now I will assume that G is invertible, but in a minute I will say a little bit more about that, why it should be invertible. But we solve that system, we plug it in the equations for C1 and C2 to recover some potential E1 and E2, and then as our sanity check, we will say, well, we will check whether the rank weight of this E1 and E2 that we recover is actually equal to T1 and T2. We can publicly check that. If it isn't, then we go to the next system, so we disregard that system. And if it is equal, then we know that we have actually recovered our correct message because the syndrome decoder that uniquely decodes to some error vector. So we know that if we find some error vector here that has the rank weight of E1 being equal to T1 and E2 being equal to T2, then we know that we've recovered the correct message. So to do a very little analysis of the attack, so first of all, we have to guarantee that such an error-free system exists, but by construction, because we iterate over all these arrangements, we iterate over all these linear combinations, we know at some point that we will encounter the error-free system. But then, of course, it's important that this error-free system can be solved uniquely to M. So we need this matrix G, corresponds to our system, to be invertible. And what we will say here is that, well, this matrix G, it consists of columns from linear combinations of columns from M, linear combinations of columns from F. We know that M was generated uniformly at random in the algorithm. So we consider these columns, these linear combinations of columns of M to be generated uniformly at random. We then have linear combinations of columns from F, and although F is not generated uniformly at random, the authors of REDOG claim that it's hard to distinguish F from a matrix generated uniformly at random. So in total, we will say that it's hard to distinguish G from a matrix generated uniformly at random. And then as a heuristic, so this is only an estimate, we can estimate the probability of G being invertible by using a result from Lange, Pellegrini, and Ravagnani from 2023. And it says that G is invertible with a probability very close to 1. And that's exactly what we want. So to go over the cost of our attack, well, what are we counting here? So this first part in the exponent, the 2 to the t1 plus 1 times t2 plus 1, are the total number of linear combinations that we have to iterate over in step 2. Then we still have some work to do for all the arrangements, which is 2 to the t1, a t2 times n minus k. And this is a rough upper bound, I will say, on the number of arrangements that we have to iterate over. And then we still have some extra factor that we have to add for the matrix multiplications that we have to do for inverting this matrix G. So we get some extra factor L to the omega times m squared. Well, in total, this is the cost of our attack. So we see that for each of the each security parameter, our attack can be. We can show that with our attack, the security of REDOG is not achieved. Well, and to conclude, so we have seen that with the Partai attack, we can construct a system of linear equations that will solve for m, well, more efficient than the claimed security of REDOG. Of course, well, there are two little topics I would like to say a little word about, which is, well, there are some small improvements still on the attack. So we've noticed that when iterating over all these arrangements, there are certain arrangements which behave alike. So we don't have to iterate over all of them. We can skip a few, and this will still save a little bit in the cost of the attack. Yeah, and then there's one remaining question. So, like, what's next for REDOG? And it's actually funny that while we were working on the final version of the paper, the authors responded by acknowledging that the attack was successful for REDOG, but they also proposed a new set of parameters for it. And yeah, we see that there is some increase in the key sizes in the ciphertext, but for us it's most important that, well, we haven't analyzed these new sets of parameters yet. So before we will endorse them, we would like to take some more time to look into that new set of parameters. And that is why I would like to conclude my talk. So thank you very much for your attention. And if there are any questions, then feel free to ask them.
All right, thank you, Mark. Any questions? Okay, I will get the ball started. So I'm going to ask, I'm sorry if you may have mentioned this and I missed it, but why is it called the Partai attack?
I haven't mentioned it. I sort of did expect this question. So on one hand, we are constructing a system where we pad equations to our attack, but of course that doesn't explain the full name here. It was actually Alex that came up with the name, and he did when he was in the beautiful country of Thailand. So it's sort of a little wordplay there on Alex being in Thailand and us padding equations to a system. So that's the honest answer here to this question.
All right, thank you. Any other questions? Okay, let's thank Mark again and thank all the speakers.